So, hello, welcome. Good morning, good afternoon, good evening, good night, whenever you happen to be. Welcome to OpenEye Cadence Molecular Sciences, Essentials of Computational Chemistry. Today, part 4, Method Comparison and Decision Making. I'm Paul Hawkins, and I will be your guide through today's wandering through, basically, statistics. I didn't want to put statistics in the title because I feared too few people would turn up. So today I promise you hopefully an entertaining look at how statistics can be used to help you in your day-to-day work, make better decisions, better understanding of your errors. As usual in these, please drop in the chat where you're joining us from. We'd like to know. And if you have any questions or comments as I go through the presentation, please add them to the Q&A, and I shall try to address them all at the end of the talk. As usual with these talks, these are going to be wide but shallow overviews. It's a lot of material, particularly today. And I'm going to cover some fairly interesting high-level topics, I hope, including the nature of probability, the importance of estimation of error, and the different ways that you can be wrong when you make a decision. So first, the nature of probability. So there are two basic ways of looking at probability. They could be thought of a little bit as like the difference between Coke and Pepsi, Coca-Cola and Pepsi. There are fans of both sides who often don't very much agree with one another. First, historically, and certainly the most widely used, might be called the classical or frequentist approach to probability, in which probability is thought of as the same as long-term frequency. So if you perform an experiment 10,000 times and you get the same outcome 10 times, then the probability of that outcome is 1 in 1,000. And this method of probability deliberately doesn't allow any idea of prior knowledge, related understanding, or intuition from the analyst. It's simply long-term probability. The Pepsi to frequentist Coca-Cola is the Bayesian approach, where the Bayesian analyst considers they have a bucket of credibility, 100% credibility, and their job is to assign credibility to different events using a mathematical formulation. And this piece of mathematics, called Bayes' theorem, requires the analyst to have some sort of prior knowledge, intuition, small-scale experiment data, and so on. So two very, very different and somewhat oppositional ways of thinking about probability, and we'll use ideas from both as we go through the rest of the material. So two types of probability. There are also two types of statistics. For example, there's been an election recently in the United States, you may have heard, and something that's talked about a lot then is sampling to estimate voting patterns. So you can't obviously ask everyone in the United States how they're going to vote. You can't weigh them all to get sort of an average weight. So you have to take a sample. And the first type of statistics is called descriptive statistics, and it simply attempts to summarize and simplify data about a sample to allow the analyst to easily understand what's in the data. The more interesting and the more difficult part is the inferential statistics, where you use the properties of the sample, say the sample mean, to estimate the thing you want, which is the population mean, but that's the thing you can't get. So then you're inferring something about the correct answer, the population parameter, from the thing that you can measure, which is the sample statistic. And then, of course, there'll be error in using the sample statistic to estimate the population parameter. So those are the things we'll be looking at today. And so I'm going to tell this sort of as a story in 6 chapters. So I'm going to have a chapter about bridges, about guys on horseback, about babies, about paintings, bad weather, and rope. So if you'd like to see how I could possibly fit all those into a talk about statistics in the next 40 minutes, please hang around. So I'm sure you know, if you have attended any of the other essentials, and certainly if you spent a little time reading the literature in your own area, that there are many, many problems for any solution in computational chemistry. So there has been a small industry of publishing data sets and tests of one or more algorithms or implementations of an algorithm to see how they perform. And part of this, of course, is to get publications, but I think more importantly, what all the operators of these different publications are trying to do is to use data from the past, retrospective experiments, to assess performance in the future. And as Niels Bohr said, predictions are difficult, especially about the future. So the first thing, the most important thing I'd like you to take away from today is this. Making a prediction without an error is a waste of everybody's time, your time and the consumers of your predictions time. And for short, I'm going to call that the Grand Forks effect. Now, for those of you who don't know, Grand Forks is a small town in the United States that sits at the junction between the states of North Dakota and Minnesota, as you can see in the picture here. And most of that border in Grand Forks is described by the path of the Red River. So the Red River runs through the town. And like most towns in the United States, the US government, the United States Geological Survey, provides a prediction to the town of the likely maximum height of flood water from the river. So in the case of Grand Forks and the Red River, the prediction was 49 feet above normal. So with this information, the town of Grand Forks took action and it spent money building a dam 51 feet high. I think you can see what's coming, unfortunately. The winter of 1997 brought a combination of melting snow upstream and heavy rain in the Grand Forks area, and the river flooded at 54 feet over normal, overtopping the dam, running into the city, causing several deaths and over $3 billion in damage. This was a massive catastrophe for the town, caused by the lack of a single piece of information, which of course was the error in the prediction, plus minus 9 feet. Now, I'm not a city planner, but I'm fairly certain that if the city of Grand Forks had had both the prediction, 49 feet, and the error, plus minus 9, they'd have taken a different action and they'd have built a bigger dam. So our whole goal for today is to avoid the Grand Forks effect. That's our sort of our first chapter of the bridge. So obviously, when we are making decisions in the real world with uncertain or sample data, we have certainty that we're uncertain. So when we're using historical data to make future predictions, how wrong are those predictions? How wrong is the sample statistic when used to estimate the population parameter, the right answer? When we make a certain decision of one way over another, what's the probability we've been wrong? What's the likely error rate? And then if we do find a difference between tools, we correctly make a decision about one being better than another. Is that just a mathematical curiosity, a statistical number, or does that difference make a difference? Does it have impact in our work? So the first of those first, using the sample statistic to estimate the population parameter or the error in the sample statistic itself. So as part of that, I'm going to reintroduce you to something I'm sure you've all studied before, the normal distribution. It's described by the equation in the top right, and it has two parameters, the mean or mu for the location and the standard deviation or sigma for the dispersion of the data. The normal distribution has some very nice properties. It's symmetrical, it's nice, and it has a fixed fraction of its probability within a certain number of standard deviations of the mean. Today, we're going to think a lot about 95% probability, and that's 1.96 times the standard deviation either side of the mean. So that's good news. We have this nice distribution with very well understood properties we can use. However, unfortunately, a lot of data in computational chemistry tool performance is not distributed normally. So here I've got some data on reproducing crystal structures with the conformation generators. This could easily be post-prediction data, measured with RMSD. So the lower bound is 0 and the upper bound is undefined. So the data here is skewed strongly to the left with a long tail to the right to high RMSD. Similarly, but in the opposite direction, measuring virtual screening performance with area under the curve, the data is skewed to the right, but has a long tail to the left. So good news in the bad news, while the data is often very skewed, if you subtract the data of one from the other, the difference in performance data, that often comes out to be normally distributed or a closely related distribution called the t-distribution. So if we'd like to use these sort of classical estimators, mean and standard deviation, we have to be aware that they're strongly affected by outliers. The old joke, Bill Gates walks into a bar and the average income goes up $10 million. So a single outlier strongly affects the location and the dispersion of the distribution. So we have two possibilities. One, a la the vase on the side here, is to make the data more relevant to the estimator. That's one approach. Or you could change the estimator you use so it's more suitable for the data that you have. So if we want to stick to the nice properties of mean and standard deviation, we have to possibly do something with our data to remove outliers. And a couple of popular techniques are known as trimming or winsorization. So the raw data here is in black, and it's again RMSD data with a long tail to the right. Trimming simply means we'd remove, in this case, the lowest and the highest 5% of the data. That gives us the data in purple. Or we could what's known as winsorize it, and we could replace the lowest and highest data with the lowest or highest non-extreme data, and that gives us these replaced values in blue. You can see here the mean in each case is decreasing as we go from raw data to winsorized to trimmed data as we're removing the influence of outliers. But again, to go to that back to that descriptive statistics idea, inferential statistics, the sample, if you believe it represents the population well, is a good sample. If you detail your sample, remove some of its data, what you have then is not anymore a sample. So you've changed the data you're operating on. So this is not something I suggest you do normally. I think what's better to do with data that we have in computational chemistry is to use a different measure. So here, the median makes a lot more sense because it's much less affected by outliers. Okay, great. Now we've made a prediction of future performance based on past performance, but we've of course not thought about the ground faults effect. We've yet to have error. So approaching the error problem, there are two general ways to do it, as there are two types of probability, two types of statistics. There are two types of ways of generating error or confidence interval estimates on things like means and medians. We can use analytical approaches, some of which involve making assumptions about the nature of the distribution of the data. Here, for example, that it's normally distributed. Or we can use what are known as robust measures that don't require us to assign a particular distribution to our data. So things like median absolute deviation, variance as a fraction of the interquartile range, and so on. So these are robust estimators that I think suit the type of data we often deal with better than the standard mean and standard deviation. So that's an analytical approach. The other is the empirical approach to error, and that allows me to introduce my next character, my next chapter, and that is this man. This is the Baron von Münchhausen, a fictional character whose life is told in a book called The Tales of Münchhausen. And in that story, it's told, as you see in the picture here, that one day the Baron went out riding, and as he often did, he went into a bit of a daydream, and he accidentally rode his horse himself into a swamp where they were both in danger of drowning. As you can see in the picture, the Baron very quickly realized the solution was simply to pull up on his own hair, and he could then drag himself and his horse out of the swamp, which he did. And this, I think, is the first explanation, if you like, in the literature of any kind, of the idea of what's called the bootstrap or bootstrapping. That is a technique that turned up in statistics in the late 70s due to someone called Brad Efron. So the logic of this idea of bootstrapping is quite simple. It says, well, the population parameter, the average weight of everyone in the United States, is inaccessible. The distribution of that data is inaccessible. All we have is the sample data, and we assume the sample matches the population well, and if it doesn't, we need a different sample. So once we have a sample that represents the population well, we try to understand variability in the population by generating synthetic data sets based on resampling our sample data. So to put that in picture form, the basic form of bootstrapping is called nonparametric. So we simply resample from our original sample at the top with replacements. So we end up with different numbers of different colored balls, different colored marbles in our resamples as we're resampling with replacements. So we get these different pictures, and then we say, well, what's the average number of blue balls, orange balls, green balls, and gold balls, and so forth. So we can then compute all sorts of sample statistics from these resamples. We repeat this process a great many times, 10,000, 50,000. And then to get, say, a 95% confidence interval, we simply look at the 22.5 and 97.5 percentile, and that gives us very easily the 95% confidence interval. So here we are using the empirical, the bootstrap, to get 95% confidence intervals on our median estimates for RMSD and AUC, thereby avoiding to some degree the Grand Forks effect. So very nice. So now I'm going to pop a few of these into the rest of the talk. I'm going to have a short quiz. We've got this 95% confidence interval. What does it mean? So does it mean that the true value, the parameter of the population, is 95% likely to be in the confidence interval? Mean that 95% of the sample data falls within the confidence interval? Does it mean that 95% of all the confidence intervals you calculate contain the true value? Is it all of those things or none of them? So this one's going to require a teeny bit of thought, so we'll give you 3 more seconds, 2, 1. And the answer is the middle one. When we compute confidence intervals, particularly through things like bootstrapping, 95% of 95% confidence intervals contain the right value. It is unfortunately not true, however, that the true value is 95% likely to be in the confidence interval. So confidence intervals are great. They help us get over the grand forks effect, but they have to be interpreted correctly. They don't tell you that, again, the 95% confidence interval is 95% likely to contain the true value. That's not what it tells you. And somewhat disappointingly, they're what you might call flat. The probability distribution across the confidence interval is uniform. You're no more likely to find the correct answer, the population parameter, at either extremum of your interval as you are in the middle. So there's no sort of shape to the confidence interval. Those caveats aside, they're very useful, and we can represent them usefully both numerically and graphically. I'm sure you've seen this many times. It's the box plot. It is a very effective way to do some descriptive statistics and graphically summarize data clearly. The median here, the 95% confidence interval, the interquartile range, outliers are shown explicitly, so at a glance you can get really good look at your data very, very easily. So here we've got some virtual screening data, the area under the curve here, higher being better, 1 being maximum. Got mean in the green triangle, median as the orange bar, the 95% confidence interval on the median, the interquartile range, and we can see immediately there are also no outliers in this data. So a very efficient and effective summary, and I'll use this box plot for the rest of the presentation. So obviously we're going to have multiple methods to compare. 2 methods here for ligand-based virtual screening, one based on the graph, one based on shape. This is called ROCS. It's a tool from us at OpenEye. If you'd like to know more about these methodologies, please go back and see Essentials Part 1. So here we have the median performance, median AUC for these 2 tools. You can see ROCS turns out to be a little bit numerically higher. So based on this box plot, would we say that the methods are different? Would we say they're the same? Do we need more information? Fairly simple answer, of course. The answer is we do need more information to make a decision about that based purely on this plot. And the information we need is what kind of study, what sort of data sets we used here. Was this a paired or an unpaired comparison? The unpaired comparison is the sort of thing we usually think about when testing drugs or other medical interventions. There's a placebo population of patients who don't get the drug or the treatment, and then there's the actual population who gets the drug or the treatment, and we compare 2 sets of different people. That's an unpaired comparison. For the most part in our area, there'll be a data set and we'll compare all the tools on the same data set. That's a paired comparison, and those are usually preferable because they control the inherent variability in the sample to reduce prediction error. So error. There are several types of errors that we can make, and there are 2 very important ones. So if we have an idea and we'd like to test it, we have 2 ways of being correct. We say, well, whoops, are the 2 things we're testing actually the same? And if they are the same and we conclude they're the same, that's the correct answer. We could also assume that the 2 methods are different, and they are actually different. We can conclude that, and that's another correct type of decision. That also means there are 2 ways for us to be wrong. If the methods we're comparing are actually the same, but we conclude that they're different, we've made what's known as a type 1 error. And if we assume that they are different, they're actually different, but we conclude they're the same, we've made what's known as a type 2 error. So if we write that down, type 1 errors are false positives. You find an effect that does not exist, you find a difference that isn't really there. Or type 2 errors are false negative errors, and you miss an effect that does actually exist. So again, 2 ways to be wrong. And certainly in the frequentist classical statistical world, type 1 errors, false positives, are considered more harmful and more costly. Now, that's a lot of text and tables. I often prefer to think about these things in pictures. Type 1 errors on the left, type 2 errors on the right. So that makes it a little bit clearer. So type 1 errors generally considered to be the most harmful, and there's a very large literature, very large set of tests to estimate type 1 errors in the classical frequentist world using something called null hypothesis significance testing, NHST, which I'm sure most of you have heard of and some of you have probably done. This has a particular chain of logic to it. You start with a null hypothesis, H0, which is usually the difference between the two things you're comparing is actually 0. Underneath, they have the same performance. There's some undefined alternate hypothesis where the difference is any other number than 0. And then, only then, do you gather data to test your hypothesis. You'll perform some significance test, an NHST, which will generate this magic thing called a p-value, which we'll look at in a minute. And then according to this value of the p-value, its size, we have a very small p-value. We're likely to reject the null hypothesis and then assume that the alternate hypothesis is true. There is a difference. But if the p-value is higher, we may not reject the null hypothesis and then assume that the two methods are actually the same. So again, to put that into table form here, we're looking to assess the frequency with which we make a type 1 error, we make the wrong decision. And the p-value that comes out of NHST does estimate the type 1 error rate under a single condition. That's if the null hypothesis that the two tools are the same is actually true. So then p-value is less than alpha. So if your p-value is less than, say, 0.05, then you would say you found a statistically significant difference. There's something going on there. There's a difference that you can use. The goal here is to avoid mistaking the variation that comes with random samples with genuine differences. We're trying to, as Nicholas Taleb said, avoid being fooled by randomness. So we have this magical p-value estimating the type 1 error rate. So again, little pop quiz. What does a p-value actually mean? Is it the probability that the null hypothesis is true? Is it the probability the data we've generated is produced actually by random chance? Does a p-value of 0.05 mean there's a 5% chance of making a mistake if you reject the null? Does it mean something else? This one's require a little bit of thought, but I'm only going to give you 3 more seconds to think it up. And the answer is, fortunately, none of the above. The null hypothesis doesn't actually mean any of those things. I think we'd especially like it to mean the first thing, but it doesn't. What it actually means is it's the probability of getting a difference between two things as big as or bigger than the one you saw if the methods underneath are actually the same. So this is the probability, if we write it symbolically, P, probability of finding D, vertical pipe, given H0. So probability of D given H0. So that's some fairly specific language. And again, it is the type 1 error rate, alpha, if the null hypothesis of no difference is actually true. So this is sort of the standard Coca-Cola frequentist interpretation of the p-value. Again, the words are not always very intuitive, especially if you're not trained as a statistician. So that allows me to introduce my next character in the story, a baby. In this case, a surprised baby. You can think about the p-value as measuring sort of the reciprocal of your surprise. The smaller your p-value, the more surprised you are to see your data if you believe the two things you're testing are actually the same, if you believe your null hypothesis. And this might be called the Frequentian interpretation. It's a little bit frequentist, and it's a little bit Bayesian, a little bit Coca-Cola, a little bit Pepsi. So we're going to look now at how we're going to be able to generate these sort of indications of surprise, these p-values. And to do that, we're going to exploit something I pointed out at the beginning, which is that while the data that we gather from our tools is often quite skewed, the difference data is usually distributed close to normal, or again to a related distribution called the t. And that allows us to use something called parametric significance testing, which is something I'm sure most of you have heard about, some of you have done, using classical tests like the t-test, or its close cousin, the z-test. And here we're making an assumption about something called the sampling distribution of the test statistic, the test data we're looking at, and we're assuming it's distributed either as a normal for z-test or a t-distribution for t-test. And then simply once we calculate the z or the t value, we just then read off the corresponding p-value from the normal or the t distribution. Very simple idea, relatively simple to calculate, and they're quite appealing for that reason. They're also appealing because parametric tests are what's known as powerful. In statistical language, that means they're able to reliably detect small differences, genuine differences, but small ones between different methods. But in order for that decision to be true, the assumption that you make about the test data has to be relatively correct. The data has to be somewhat similar to a normal or a t. If you don't believe that's true, or you don't want to make that assumption, then you're going to have to do something called nonparametric testing. And that brings me to one of my favorite slides in the talk, this one, because it allows me to say my favorite test in statistics, and that is the KS test, the Kolmogorov-Smirnov test. Pretty fun. It looks at difference in cumulative distribution functions, CDF, shown here. Another related test we'll use in a second is called the permutation test, and that actually builds the sampling distribution of the test statistic as it goes. These tests, non-parametric tests, are appealing because we don't have to make assumptions about data distribution, but as you'll see, they're uniformly less powerful. They're less able to reliably detect small but genuine differences. So let's put these to work in our virtual screening comparison problem. So we have our 2D method, max, our 3D method, rocks. Here we're looking at the green triangles, the mean performance. The t-test exists to test differences in the mean, which is here 0.039. So we run the t-test and we get a pretty low p-value, 0.0025. The baby is quite surprised to see this data because the baby believes the two methods are actually the same underneath. So this data seems to indicate that perhaps the null hypothesis isn't true and we should reject it. We can perform the same sort of test with the permutation test, which actually again builds this sampling distribution directly, and that returns a p-value basically 10 times higher, 0.025. The baby's a lot less surprised. There's a lot less difference between these methods indicated under this test because, again, it's less powerful. So different advantages and disadvantages to both. Another sort of ramification for this is, of course, as I said, there are usually more than two tools that you'd like to compare. So often you'll have data like this. Some nice descriptive statistics here, some box plots for data looking at sampling conformations of macrocycles. And there are 6 different tools here. So we actually have 6 sets of data. We're using robust statistics to get indications of location. That's the median, and dispersion, the median absolute deviation. We can also compute the number of outliers. Now, if we have 6 tools, 6 sets of data, we want to do all the pairwise comparisons. We have 6 times 5 divided by 2. We've got 15 separate comparisons. It's quite a lot. So if we're doing 15 comparisons and we want our type 1 error rate to be 5%, what's the chance that if the tools are actually all the same, we find that one of them are different? So if they're all the same, but we incorrectly find one that's different. What's the probability of that? 5%? 12.5%, 26.4, 53.6, or 85%. Now, this is going to require some calculator work, so I'll give you the answer. It's 53.6% calculated that way, where alpha is 0.05. So there's more than a 50-50 chance we incorrectly conclude that one tool pair, there's a difference if in fact they're all actually the same. But that's an unacceptably high error rate. So there's been a lot of work in the statistics community over the years to try to reduce this chance of what's known as false discovery. So we can use mathematical methods to control false discovery rate, or a related but a non-identical thing called the family-wise error rate. And there are some different methods here that I point out. The oldest is due to someone called Bonferroni, where he just said, well, if you take the type 1 error rate you want, say 0.05, you just divide it by the number of comparisons. This leads to a very low adjusted type 1 rate, which leads to very high type 2 rates, as you'll see why later. So that's what's called overly conservative. Other examples exist. For example, to generate the data I have here in this matrix, I use something called the Holm comparison. So here we have sort of 3 classes of result. In brown, there's no difference between these tools. In a deeper purple, there's a clear difference between the tools we've achieved, so high levels of statistical significance. Our p-values are very low. And then in a couple of cases, we've got these somewhat marginal p-values where the baby's only relatively surprised to see this data if the baby believes the 2 tools are actually the same. So we've got some statistically significant differences here, which we can, I think, rely on. But again, this has required us to make some assumptions about data distribution, control for multiple comparisons on this, some quite complex operations going on here. And we might prefer to simplify our thinking about what's happening. So to do that, we can go back to our friend the Baron and our bootstrap confidence intervals and just look at the overlap or otherwise of the confidence intervals. So here, for example, the upper bound of the 95% confidence interval for max is 0.73, and the lower bound for rocks is 0.726. So the confidence intervals actually overlap. So actually, does that mean that rocks really is better, or are they actually the same? Again, unfortunately, we need more data about the comparison. We need to know if this is a paired or an unpaired comparison. It's a paired comparison, so we can't just look at the confidence intervals and say, oh, they overlap, there's no difference. We need to look a little bit deeper. But we can take the same idea that we can generate a confidence interval on an estimator, but in this case, it's not the actual estimator, it's the estimator on the difference. So here we're going to make an analogy with the t-test, which looks at difference in the mean. So here are our means in the green triangles. The difference in the mean is 0.039. We can generate a bootstrap confidence interval on the difference. The upper bound there is 0.065, the lower bound just below 0.01, more than 0. So we can say then, from a rather different perspective, I am 95% confident that rocks outperforms max, because the 95% confidence interval doesn't bracket 0. And that's known as inference with intervals. So of course we can do this pairwise. We can of course do it on a multi-level comparison. So here we have 6 tools. We're comparing them to the one on the left. What we have for each of the 5 comparator tools is the mean difference, and the black bar is the 95% confidence interval from our friend the Baron. So you can see in 2 cases, there's a clear difference. One tool works better than these 2. In the 2 other cases, the tools are clearly the same. And then there's one tool here where we have possibly a marginal difference. And the reason that this might come about, I'll get to in a little while. So we're sticking with this idea of looking at p-values. We'd like this idea of significance. So some p-values you generate are going to be significant. But obviously, like there are 2 types of statistics, 2 types of probability, there are 2 types of p-value. And the other type of p-value is it's a not significant difference. And that can actually mean 2 things. Either there is no difference, excellent, we did well, or that we committed a type 2 error and we missed a difference that really exists. How could we assess what our type 2 error rate is? So that brings us to my next chapter, my next character, power. So the power of a test is attempting to control its type 2 error rate, that if the things are really different, we're trying to avoid concluding that they're actually the same. So again, the type 2 error rate here formally is the probability the test will correctly lead to rejecting a false null, where the null is the 2 methods are the same. So the type 2 error rate is beta. The power of the test is 1 minus beta. So again, type 2 errors historically are considered less harmful. So our minimum beta is actually quite high, it's 0.2, or that gives us a power of at least 0.8. So we're 80% likely to reject a false null. What we're trying to do here, of course, is avoid missing genuine differences. So both of these things seem appropriate. We'd like to avoid false positives, type 1, and false negatives, type 2. Unfortunately, the 2 error rates are inextricably linked with one another. So if we look here, the green vertical is a particular critical t-value. The area under the red curve, which indicates the confidence that the null hypothesis is true, is our type 1 error rate, usually 0.05. So if we want to make our alpha type 1 error rate smaller, we move the green bar to the right. What happens then is the area under the alternative is true, which measures the power, gets larger. So as alpha goes down, beta goes up. If we move the bar to the left to make beta smaller, alpha rises. So the 2 go exactly opposite. The only way we can have lower type 1 and lower type 2 is to increase the sample size. So it's a very simple equation we can use to estimate the number of samples, number of test systems we need. That's the alpha and the beta. So of course, the smaller these 2 are, the larger n will be, divided by something called the effect size, which is an indication of impact. We'll get to cover that in a moment. So a very simple idea, very simple formula, not a lot of mathematics to it. And this is a foundational activity in all clinical settings, whether you're looking at animal studies or human studies. The first thing the analyst will do is decide how many people, how many test subjects need to be in the study. There's no point in doing the study if there are too few, because you then run the risk of making type 2 errors. And there's obviously very significant cost in using too many in terms of mechanical costs, operational costs, and costs in human suffering. So it's very important to get the sample size correct. It's again, foundational activity in clinical studies. And basically, in our area, in computational chemistry, this is never done. So the second thing I'd like you to take away from today is always think about your sample size. How many test systems do you need to accurately make predictions about comparisons between different methods? So let's go back and again apply power, a retrospective power analysis, to this comparison. So we concluded there's a genuine difference here between Max and Rox using a number of different methods, both parametric and non-parametric tests. However, if I take the effect size, which I'll get to in a minute, that I actually found, and I go back and I calculate the power that I got, what I ended up with is my power was only over just a little over 50%. There's a 46% chance of a type 2 error that I'd have missed an effect that genuinely exists. I ran this experiment on 97 separate virtual screening data sets, actives and decoys. In order to get an adequate power, 0.8, type 2 error rate of 0.2, I'd have needed about a 60% larger set, over 150 samples, to adequately power my study. So again, this is a thing we never think about, and often I think that's to our detriment, that we often miss effects that exist because the studies we're performing are underpowered. And we are unfortunately, by no means alone, citation there to how underpowered studies are having poor effects in clinical work also. So we've talked a lot up to now about error rates and statistical significance. So why have we done that? Well, that brings me to our next chapter, paintings, and of course that's a self-portrait of Vincent van Gogh. And Van Gogh had a long correspondence with his brother Theo, who was an art dealer. And in one of the letters to Theo, Vincent van Gogh wrote, "The great is a succession of little things that are brought together." Certainly this is a thing that is very much part of our lives at OpenEye as software developers. I think this is a difference between software development and tool use in a professional computational chemistry environment. As developers of tools, we're very interested in incremental performance. Rarely does a developer have an idea for a tool that causes a huge leap in performance at one iteration. So as we are making relatively small changes, small improvements, we want to make sure that each of those improvements is genuine, so we build on top of a firm foundation. We add several small changes together that make one large impactful change. So we're looking for substantively significant, but those only usually occur after adding together a small set of statistically significant differences. So to point out the separation between statistical significance and substantive importance, I'm going to use a paper from a journal you've probably never heard of, Nature. They publish all sorts of things. One of the things they published, a paper back in '98, looking at an analysis of the heights of men going into the Austrian army. 500,000 men, and the study concluded with a very, very high confidence, a very, very small p-value, strong statistical significance, that men born in the spring are taller and men born in the autumn are the shortest. Very, very small p-value. Now, if you happen to just go on and read the next sentence of the abstract, I think you'll see the problem in the paper. That is in the concluding phrase here. The difference between the tallest men from the spring and the shortest men from the autumn is 0.6 of a centimeter. Now, again, I've never been in the armed forces and certainly never in the Austrian army, but I am quite certain that a 0.6 centimeter difference in height has no impact on one's performance as a soldier. This is a statistically significant but unimportant difference. So that leads us to this idea of how can we estimate if a difference makes a difference. It's a very simple approach to that, developed by someone called Jacob Cohen. He termed it the effect size, called it D, and it's simply the difference in the mean performance of the two tools divided by their pooled standard deviations. We had a publication lately from Anthony Nichols here at OpenEye, which estimated with a very simple formula what the standard error on D is, just the square of D divided by the number of entries in the sample, N, and then derived a very, very simple formula that says, well, over time, what's the probability that tool B outperforms tool A on the basis of the effect size? It's a quarter of D times 0.5. There's a related, a fairly simple formula also called common language effect size. Both of these allow you to make statements like this. Based on the effect size, the probability that one tool outperforms another, in this case ROX outperforms Max, is 57%, and again with a confidence interval 95 of 5%. So standard sort of statistical thought thinks D should be at least 0.2 or higher. So this is a significant effect, not a large one, but it's substantive, I should say. But again, it has an error, it's quite large. And so we have this situation where we have between a 62 and a 52% chance that ROX will outperform Max over the long term. That, I think, is news that we can use. Probabilities and confidence intervals and so on can be hard for us to think about. But the probability that one tool outperforms another over the long term, I think, makes a great deal of sense. So that now brings us to a fairly subtle difference between tools that are identical, non-identical, and equivalent. And this is my last chapter in the story. This is the rope. So as I told you earlier, we can make conclusions based on things like confidence intervals on difference, inference by intervals. And this tells us that these two tools are not identical. I'm more than 95% confident a difference exists. But is that difference making a difference? So this allows us to use something called the region of practical equivalence, or ROPE. So all I need to do then is decorate my analysis, my plot here, with this region of practical equivalence. And say for AUC, I will say there's got to be at least a 1% difference in AUC either way. And if there isn't, with confidence, I'm going to say the two tools are functionally equivalent. So here, our 95% confidence interval does bracket my ROPE. So I could say then, I am less than 95% confident the difference is important. The two tools, while they are not identical, are functionally equivalent. So we've looked a lot at making confident decisions with error rates, p-values, and so on. I sort of conclude this section with a quote from a paper by John Sen, which he calls 2 cheers for p-values. So there are some substantial conceptual problems with classical null hypothesis significance testing, and I write down some of them here. I think the two that I'm really most interested in is the point hypothesis, you're testing exactly a zero difference, and that the p-value doesn't indicate the probability of your null hypothesis. So that brings me back to the Coca-Cola versus Pepsi frequentist v Bayesian approach, and to this very famous equation, Bayes' theorem. So Bayes' theorem allows us to use the word in statistics that I think is the favorite for all middle school boys, and that is the posterior probability that a given hypothesis, theta, is true given the data that we have, the p of theta given data. And we need 3 things to calculate that. We need the p of the data given the hypothesis, it's called the likelihood, the probability of the hypothesis before the data, so this is the famous Bayesian prior that the analyst needs to provide, and then something called the marginal, the probability of gathering the data. There are now mathematical methods to calculate this, and they work really quite well, but there's a lot more complexity to that mathematics compared to standard frequentist testing. So if we believe that the data we're analyzing is distributed, say, as a normal, then we're going to have to, in order to do Bayesian analysis, understand what the mean and the standard deviation of that might be, and what the range of possible values for the mean and standard deviation are, and how they may be described as another normal, a uniform, and so on. So there's a lot of thinking that needs to be done in order to set up a Bayesian analysis, but it provides, I think, very useful answers. We can generate, again, the middle school boy's favorite word, the posterior probability of the hypothesis, the probability of the hypothesis given the data, P of H given D, and we can assign credibility, again, that Bayesian bucket of credibility, to a range of different parameter values. So to conclude, we're going to look at the Max v ROX difference here in a Bayesian analysis. We're going to generate the probability that the mean difference falls at a certain point or in a certain range, and that's the blue curve here. The equivalent in Bayesian thinking to the confidence interval is called the HPD, the highest probability density, and you can see it's very different to the confidence interval we generate with classical statistics. And again, what we're looking at here is the posterior distribution in the difference in the sample means. So to estimate any particular value of that difference, we simply read it off of the graph or integrate the graph above a particular value. So this is another, and I think very powerful way of avoiding the Grand Forks effect. It allows us to assign probability to a number of different outcomes in a single analysis. Okay, so let's wrap up. We looked at bridges, the Grand Forks effect, the importance of estimating error, however you do it. In the classical world, we looked at the Baron, the idea of the bootstrap as a powerful way to generate reliable confidence intervals for data of any particular distribution. We looked at babies, the idea that the p-value from traditional null hypothesis significance testing is intuitively a measure of our surprise. We looked at painting, Van Gogh's idea that we build great things from a series of small things. We build small but significant, statistically significant differences with a high level of surprise. We looked at power, so trying not only to control false positive rates with our p-values, but control false negative rates by making sure we have an adequate number of samples, an adequate data set for our comparison. And then lastly, we looked at the idea of the difference between statistical significance and practical importance, and the difference between non-identical and functional equivalence. So thank you very much for coming along with me on the journey. There will be a Q&A session in a few moments, so please hang around for that. I'd like to take any questions you have. And for that, farewell temporarily. See you in a moment. Okay, so thank you very much if you've decided to join us for the Q&A. We've had a couple of questions come in. One of them is about the difference between the Bayesian and the Frequentist p-value. Like, is there an equivalent of something like a p-value in Bayesian thinking? And the answer to that is no. There is not an equivalent to that. You can, again, using that posterior distribution of probabilities, you can estimate the probability for any particular outcome, but that's up to you to decide. That isn't something that the test automatically returns. So that's sort of, again, on the analyst. Again, that difference in thinking. And, oh, that's a good question. So I talked a little bit about the frequentist approach to effect size, the difference, making a difference or not. The question is, can we do something equivalent to effect size in the Bayesian? And the answer is yes, mostly, but I will say it's quite complicated to do. There is code, there are methods out there to do it, but it is quite complicated. I feel that it's something that you have to be quite an expert in Bayesian analysis to do. So the frequentist thing, I think, is a lot easier to think about, and it gives us most of what we want. You can get a more detailed, a deeper analysis in the Bayesian world, but it is harder to do. So that's a good question. That's actually all the questions that came in. So I'm going to conclude the session there. Again, thank you very much if you stayed around for the Q&A. And if you have further questions that come to you afterward, please drop us an email and I will attempt to answer asynchronous. In the meantime, goodbye. Thanks very much for coming.